The first one I want to do is prove an algebraic law about a data type. So I'm going to define something called a bit. It's got two constructors, I and O. This is meant to be 0 and 1, of course. What I want to do is write a function that does a bitwise OR over this data type. So I'll just implement this. We'll see how we go. So the implementation, we have to see something about x and x1. So Idris allows us to deconstruct these things and create a pattern match on it. So in the case that we've got O, then that should be x1. And in the case of I, that should just be I. Does everybody agree that this is OR? Please don't, because I'm going to prove that this is somewhat in the right direction. So what a property of OR is that it's associative. So what that means is that A or B or C equals A so that's the associative property. And we should be able to prove that that is the case. It's not going to prove everything about the OR function. There's a lot more that we could prove, but this is one step for proving our property of this OR function. So we know that if we were to prove this, we know that at least we didn't stuff it up that badly. We might have still stuffed it up, but not that badly. So I'm going to make a function called OR associative. It takes a bit, another bit, and another bit. And this code I wrote just here is actually exactly what we want to prove. That's actually an Idris type. The type is that these things are equal. That's actually a type in Idris. So the first thing, if we load this up, Idris says we're trying to prove this thing, which is exactly what I wrote down. And we've got A, B, and C in scope. Now, it doesn't know what the A, B, and C's actually are, so what we can do is, again, pattern match, load this up, and now we've got different things that we have to prove. So we have to prove that OR B and C is equal to OR B and C. That's pretty easy, right? So there's actually a constructor called refl in Idris that does exactly that. When two things are exactly the same and Idris knows that they're exactly the same, they actually show it to you as being the same thing. It's the same thing. Refl is that thing. The other goal that we had to prove was that I equals I. I think that's pretty easy as well. What I'm actually doing is pressing Control-C, Control-A. That gets Idris to do a proof search. So it'll actually find the proof for me. I'm not actually typing it. Like, Idris is constructing my program for me. All I have to do is pattern match, and it found the program for me, which I think is pretty awesome. Now, OR probably isn't very practical, but I've got a little bit more that we can do. So we've got this bit string, which is a list of bits. And see how I've just defined a type as if it was just a value? So what we'll do is make, we'll call it BSOR, just because. So this will take a bit string, another bit string, and return a bit string. So this is like OR, but with whole strings rather than just one. And again, we'll get Idris to, we'll see what Idris will pattern match for us. And so what we'll do in this case is just accept whatever Idris has given us. I don't know. I'm just making this up. I don't think that's right, though. Is that right? I think it's basically right. In this case, though, this is going to be a bit more interesting. We don't want to accept whatever Idris gives us. So this one will OR these two. And then what do we want to do? Something like that. I don't know if I'm doing it right, but Idris will hopefully help me out in a minute. So we've got this bit string OR. I've tried to implement OR over bit strings, not over just a single bit. We'll do basically what we did before. Except now we're working over bit strings rather than just a single bit. So everyone see that what we're doing? We're doing it over bit strings rather than just bits. So we're proving the associativity of whole strings, bitwise or over whole strings. So Idris is going to tell us what we need to prove, which is exactly what I just stated. And what we can do is just accept whatever Idris is going to give us. So in the case that we've got an empty, we've got the empty bit string, then it's the same. Like it's just BS or B and C. And we just keep deconstructing each of the fields. And in any case where we've got an empty one, we're done. Once we get an empty bit string, we can prove that those things, it's just using the other two. Now this one's a bit more interesting. So this one's asking us to prove that these two things are the same, and there's multiple things going on here. So there's the associativity of OR, which is different, and then it needs to prove the associativity of the rest of the list. So what we can do is come up here, and Idris will ask us to start proving things. So Idris got two languages in it. One of them is the Idris language, which you can write at the value level and the type level. But then it's also got a tactic language, so you can actually write proofs in a different sort of language, which is a bit more familiar with, for most people, and also a little bit more succinct for a lot of the cases. So here's the goal that we have to prove, that OR and OR is associative. We can see that they're different, and we need to make them the same thing. The goal is to make these two things the same thing, these two ORs. This one and that one. So we've already proved that OR is associative, right? So what we can do is rewrite that goal with our proof. And you can see that, can everyone see the difference there? So we've proven that the first part is the same. So we're partway there. Now what we should also do is prove the last part. Do those things look the same now? So we've done it for the second, we've proven that the first part of this list is the same. We've proven that the tail of it is the same. So what we can write now is trivial, and here's the best part. You write QED. And there you go, Idris sets that out. So it's proven that, that our bit strings are associative. I at least got that much right. I might have gotten some other parts of the algorithm wrong, but I've at least proven this property. I could prove a lot more about it, but I'll stop there and move on to the second part. So that goal was like correctness. We could prove certain properties about our program. What I want to show now is the expressiveness of dependent types and try and implement something that you probably couldn't do unless you had macros. It's actually one of the motivations for things like macros. So I'm going to make something called a bin char. It's indexed by a character. So we've got a value at the type level here. And we'll do something similar like we did before. So this will be a bin char, and we can actually use a character and put it at the type, put it into the type. That one should be a 1. There we go. So now we've got these two constructors, and they've got a value thing in the, they've got a value at the type level. So now what we need to also do is have some, I want to make a proof that everything in a list can be of something. Hold some sort of predicate. So this predicate is actually going to be from some value into a type. That's going to be how we predicate a value. And then I'm going to have a list of those things. So the proof, so we'll have a list of the values and also the proof that a particular value, we'll have a proof that the predicate holds for each of those values. This curly brace is actually for saying something's implicit, so you don't have to give it each time when you construct this. Idris will try and figure it out for us. So we'll have some predicate, and I can make an every. So if you give me an empty list, that predicate holds. If you give me a cons, and then you have to give me a value you have to show me the predicate that value holds for. And then give me the tail. Oh yes. Thank you. So what we've done here is said that for a value that the predicate holds for, and a tail for the rest of the list that this thing holds for, then we can just put that value onto the list and say that it holds for everything in that list again. Now I'm going to write a function that says for every bin char in some list, we can get out, and given a natural number, we can get out a nat. So this is going to be converting from these binary characters into a natural number. The nat there is going to be an accumulator. So again, we'll split. And what we have to do is actually split a bit more than this, because what this wants is, what we have in scope is just some bin char. We want to actually do something a bit more interesting than that. We want to see what type of bin char it is. So in this case, we just want to recurse in the case that it's O. It doesn't actually, so it's 0. It doesn't actually add anything to the number. And we're just, this accumulator is the, the count of how many bits we have. So we're just decrementing that. But in the case that we have I, we want to actually raise 2 to the power of k, and then recurse. I don't know if this is the right thing either. I'm sorry. But what we can do now is that given a string, we can also ask for a proof that everything in that string is a bin char. And so I can't remember the name for going from a string to a list of characters, but what I can do is search for it, if you can see that. So it just kind of has like a built-in Hoogle into it, which is pretty cool. And so we can see here that there's something called unpack. That's the one I want. So I can just type unpack s. So what I'm doing is unpacking the string that we get as an input and asking for evidence that everything in that string is a bin char. And that should print out a nat. So what we can do is, here this is actually using the proof, so we can actually use the proof at the value level. We can actually say, so this was going to be the from bin chars and something like that. So I should be able to load up the REPL now. Right, so Idris doesn't find the evidence. It doesn't automatically find the evidence that every character in that string is a bin char. So Idris actually has a feature, and you can just put auto before that, and it'll do the proof search, like I said before, how we're searching for proofs. It's going to do the same thing. It's going to try and see if it can construct a bin char for every character in the list. So if I reload this code should now work. Supposedly that's 23. I don't know if that's true. I know that's 3. So you can see that we've kind of made literals in some sort of sense, because we can't type in that. Idris is not going to be able to find evidence that that's a bin char, because none of those digits have bin chars. And and it will only work if you put in things like that. What we can actually do is say, well, what's this? Is this 5? It's 4. Let's go 4. And so if we go example 1, so it'll say it's a compilation error, and it'll actually give us the real thing. So we can actually even leave examples of our evidence, of our program inside as types, and say this thing holds true. And if we were to modify any of our functions, it would only compile if this also compiled, which I think is pretty awesome. You can leave examples in and only make it compile if the value level holds, which is pretty cool. And so I've got one more example, and this is probably my favorite one. So I was looking for some sort of example of computational complexity, so I asked my coworker, what's something that you've done recently where the computational complexity wasn't very good? And he was describing this algorithm where he had to compute things over days for every day, and so every day depended on the previous day. So for day 1, it depended on day 0, which didn't exist. So he computed for day 1, day 2 depended on day 1, and then day 3 depended on day 1, day 2. So we can see that this is growing in a bad way. This is actually factorial complexity. And I'd like to prove something has a factorial complexity, which I think is pretty cool. So what I'm going to do is try and make a data type called cost. So we're going to make a data type called cost. It takes some sort of type, and it also takes a nat. The nat is the actual cost of what it takes to compute that value of that type. But the constructor won't actually take the cost. Because it's at the type level, we don't really care. Carrying it around at value level, we don't have to do that. We'll just carry it around at the type level. We don't need to carry around the runtime cost at runtime. So we'll make a function called uncost. We'll take a cost. Idris just wrote my program. That was pretty cool. But this will take the value out of the cost, this cost data type that I've just created, so we can just use it without having to worry, without having the type be contain the cost. I'm going to make this a monad. There's an interesting reason why. I'll get to that in a minute, but we'll make the return just take a t and give us any cost. So we can return, like, if we wanted to say return and say the cost is 1,000, we can do that. We can make any value, any cost, which is a problem, and it should probably be private, but I'm sorry. Okay. So I'm going to write a monad. So this is going to be the bind. So given a cost, what should the cost of this monad be? Anyone take a guess? N plus m, which is pretty cool. So if we have these dependent computations, it's just the cost of doing those, both of those. I'm doing something not very nice here, but so we calculate something. We calculate the B cost, so the cost of doing B. We actually remove the cost completely, and then we say, well, the cost is actually n plus m. So here I'm doing something a bit loose, and I'm just saying, trust me, it's n plus m. It's just something that I've defined. The monad is n plus m. I could do n times m, and Idris will just accept it. So there's no verification here. This is just I'm just stating that bind means n plus m. So what I want to do is write a function that says, given some, tell me to do something n times, and something that costs something, and also initial value, like an accumulator, then the cost should be, anyone want to take us to this? If we're doing this cost n times, what should the cost be? Yeah, so the cost is just going to be doing that thing n times. It's really simple. So in the case that we get to the end, so we've done things n times, this is the base case. In the case that we've gotten to the end and we need to do things 0 times, then we can just return it and say the cost of returning this value is 0. So this return is actually, the type of it is going to be cost of 0 of A. In this case, we can start using the do notation. This will be the cost. This will be the accumulator. So if we do the thing, if we get the value out of the cost that we get passed in, then we also want to recurse and do it a few more times and just append these things together. I'll do accumulator plus. So Idris has just verified that that is in fact n times n. This should not compile. There you go. Yeah, so we haven't proven that. It's asking for a proof that, sorry, it's saying that that they're not the same thing. That n is not n times m. It means I'm not actually saying that, but that if you keep going and keep increasing the bounds, that's what you get to. So going back to my coworker's problem, he said that for n days, it was a factorial, the cost was factorial. So I want to, this isn't his problem. This is not what he was trying to do. But I want to show something with complexity of factorial. String. So we should be able to construct some sort of value that has this cost, has a factorial cost. So I don't know, this is a function that should theoretically, yeah, it type checks. So it does something factorial n times. This is because we're recursing over doing the day, and we're also doing it n times. So I'm just going to show what this outputs. So if I ask for the day 0, so you can see that it's climbing up in cost. So it went from cost of 2 to cost of 24. Say cost of 5, that's gone up to 120, right? Yeah. And you can see that it's making some big string. What if we ask for day 7? It's kind of costly. So this is some huge value. Is it like 5,000 or something? I don't know why I've got all these blank. Here we go. So it's some huge string that we probably don't want to ever compute. So theoretically, we should be able to bound this and say, never compute anything that's, what value did I put in? 7. Should never be able to compute anything more than 7. So theoretically, I can make all of this private and only expose this function where I say, only do things that are less than 7. So there's a function like, that can go from, so fin is actually, there's a cool feature in Idris here, if I can remember it. Here we go. So we can say like, we can ask for documentation. So fin is something that's less than some bound. So we can say fin of 7 would have to be some number less than 7. So we can run programs as long as you give me a number that's less than 7. And there's also, so fact takes a natural number. So I need to go from a fin of n to a nat. And here we go. There's a function for that. And that's going to give us a string. So we should be able to do that fin to nat thing again. And if we load up the REPL, so if you only use run, or if we only exposed run in this module, we could run anything that's less than 7, but we can't run anything more than 7. Or we can't even run 7. It has to be less than. So it's pretty cool that we've proven that, so first of all, we've proven that the cost of evaluating this function is factorial. So the computational complexity is factorial. It doesn't necessarily have to be computational. We could theoretically make this memory, so the memory usage would be factorial. But we've proven that it's factorial, and we've also proven that we've also made a function and made it so that you can't run factorial for anything greater than 6, which is pretty cool. So we're guaranteed that the runtime is within some sort of bounds. No, is anybody impressed by that? I was. It's pretty cool. Yeah, so